Today we have this really cool integral that we're going to solve using contour integration. So for reference purposes, let's call the integral we have I, and we need to define a complex valued function f of z. And judging by the structure of the integrand, we need the squared logarithm of z divided by square root z times 1 minus z squared. Now, it may look like there's a singularity at z equal to 1, but that's not the case. Why? Because the squared logarithm of z and 1 minus z squared both have zeros at z equal to 1. So that means the limit as z approaches 1 of this thing here is defined. The limit exists. However, there's a singularity because of the squared logarithm and, of course, the square root z in the denominator at z equal to 0. So that means we have one branch point to take care of. Now to define a suitable contour. So we need to draw the complex plane first. And we have this branch point at z equal to 0 that I'm going to shade in green here. And we'll define the branch cut to be along the negative imaginary axis. Okay, cool. So a suitable contour would be the classic semicircular contour. That keeps things nice and simple, right? So we traverse the negative real axis first and then skip around our branch point. We continue along the positive real axis and then loop back using this big semicircle. Okay, that's not a bad drawing by neat shapes here. It looks rather nice indeed. Okay, so let's give names to everything right now. So the radius of this big semicircle is r, so you have negative r here, positive r here. For the little semicircle, the radius is epsilon, so negative and positive epsilon here. And let's name this little circle lowercase gamma and the bigger one uppercase gamma. And everything in the contour, the whole contour is going to be called C. Everything in the contour is nice and holomorphic for our definition of f of z. The function is nice and holomorphic here. So that means the integral on the closed contour C by Cauchy's residue theorem evaluates out to 0 because there are no residues anyway. Okay, cool, but how does that help our cause? Well, first we have to break down the contour. So we realize that there are a number of integrals to evaluate here. So the integral on C equals one integral from negative r to negative epsilon, plus an integral over lowercase gamma, plus an integral from epsilon to positive r, plus an integral over uppercase gamma. And we're interested in the cases of r going to infinity and epsilon going to 0. So the integral on the left-hand side here is just 0. And what about the other four integrals? Well, let's first take note of this integral, the one along the positive real axis. Well, in the limit as r tends to infinity and epsilon tends to 0, this integral equals the integral from 0 to infinity of exactly our function with the z's being replaced by x's because we're moving along the real axis. So we have the squared logarithm of x divided by square root x times 1 minus x squared dx, which is in fact our target integral I. So let's just replace all of this by I. And what about the integral from negative r to negative epsilon? Well, once again, in the limit as r tends to infinity and epsilon tends to 0, this integral here becomes the integral from negative infinity to 0 of log square x, again because we're on the real axis, divided by square root x times 1 minus x squared dx. And now let's perform a transformation, but first I have to zoom out a bit to get a better visual of things. Okay, cool. And I messed something up there. It's fine, it's fine. This is I. Okay, so I'd like to now perform a transformation from the x realm to the negative x realm. In that case, I have the integral from infinity to 0 of the squared logarithm of negative x divided by square root x becomes I times square root x, correct? So we have I times square root x, and 1 minus x becomes 1 plus x squared, and the differential element now becomes negative dx. And you can get rid of the negative sign, of course, by switching up the limits of integration. So you're integrating from 0 to infinity again. Okay, cool. So what exactly is the logarithm of negative x? Well, log negative x equals log x plus log negative 1. And what's wrong with these two logarithms? They look horrible. Sorry about that. So log negative x equals log x plus log negative 1. And negative 1 is, of course, e to the I times pi as per Euler's identity. So that means we just have log x plus I times pi. And all of this is squared. So that means taking the square of everything, I have the squared logarithm of x plus I squared pi squared. So that means I have negative pi squared plus 2I pi times log x. So plugging in this information into the integral, so the integral from negative r to negative epsilon in those two limits equals the integral from 0 to infinity now of the squared logarithm of x divided by square root x times 1 plus x now. Yes, that's correct. And wait, you have this I being multiplied as well. So that becomes the reciprocal of I is, of course, equal to negative I. And you have another integral here, minus I times the integral from 0 to infinity of pi squared divided by square root x times 1 plus x squared. Okay. And one more integral. You have a plus sign, 2I pi times this factor of I there already, negative I, that is, times this factor of negative I. Yeah, that's correct. So you have I squared, negative I squared, which is a plus 1. Okay, cool. So that means this is just 2 times pi. 2 times pi times the integral from 0 to infinity of log x divided by square root x times 1 plus x squared dx. Before we plug in the newfound information in green into the equation we have, allow me to make one correction first. This should be a plus I times the integral because we had negative pi squared and we multiplied the integral by negative I. So the two negatives cancel out. So yeah, everything seems to be in order. Wait, it's 1 plus x squared everywhere. Okay, cool. Now let's make an analysis of the integral over the contour, uppercase gamma. The limit of the integral over gamma as r approaches 0 is 0. And I'll leave the verification to you as an exercise, but of course I'll provide some hints. First up, any complex number z on this contour can be parameterized in the polar form as r times e to the I phi, where phi varies from 0 to pi. And recall the function f of z. F of z was the squared logarithm of z divided by the square root of z times 1 minus z squared. So an analysis of the modulus of this function revealed something. Notice that in the denominator we have this quadratic polynomial in z times the square root of z. So we know that the function in the denominator will outgrow the logarithmic function in the numerator. We know that from basic calculus, right? So that means in the limit as r tends to infinity, this modulus tends to 0. So that means the integral of the modulus of f of z approaches 0 as r approaches infinity, which implies that the integral of f of z over the contour gamma in the limit as r approaches 0 is 0. Okay, cool. That means we can just cross this out. And a similar argument holds for the integral over lowercase gamma in the limit as epsilon approaches 0. And again, I'll leave the details as an exercise for you, but no hints are required over here. I mean, the parameterization is exactly the same. Just replace r by epsilon, and of course you will need to use one limit from basic calculus, that the limit as epsilon approaches 0 of epsilon times log epsilon is 0. So yeah, we can cross this out as well. And that means we have a much simpler scenario at hand. We have on the left-hand side 0. So this implies that I equals negative limit of the integral from negative r to negative epsilon as r approaches infinity and epsilon approaches 0. Again, I've copied down the information in green for more clarity. So here's what we know so far. I equals the negative of this limit, and this limit equals all of this stuff. So let me just introduce that extra negative sign that reverses all the signs we have. So I have negative signs here and here. And let me just club these two integrals together as the imaginary part of the result on the right-hand side. So I have I times the integral from 0 to infinity of this logarithm thing minus the integral from 0 to infinity of that pi squared thing. You get the idea. And it's worth recalling what the integral I was. Well, that was the integral from 0 to infinity of the squared logarithm of x divided by the square root of x times 1 minus x squared. So I is the integral from 0 to infinity of a real valued function of x. Hence, its result is a real number. So I is a real number, and I equals this limit, and this limit has a real and an imaginary part. So what makes sense is that the imaginary part just evaluates out to 0, which is awesome. So that means we have the result of I equaling negative 2 pi times the real part of that limit, which is this integral that I'm going to call I sub 1, and I'm going to evaluate that using another application of contour integration. So yeah, this is fun. So here's I sub 1, the new star of the show. First, let's make a substitution to make our lives easier. Let root x equal u, which implies that 1 by root x dx equals 2u du. And this implies that I sub 1 equals twice the integral from 0 to infinity of log of u squared, which of course equals 2 times the, oh, terribly sorry about that, 2 times the logarithm of u. So you get 2 times 2 is 4. And 1 by root x dx is the new differential element du, and you have to divide all of this by 1 by u squared squared. And we're going to evaluate this integral once again using the semicircular contour. There it is, a familiar face always welcome here. And everything looks pretty much the same except for the complex value function f of z being defined now as log z divided by z squared plus 1 squared. And in this case, you do have a pole enclosed by the contour because z squared plus 1 equals 0 implies that z equals plus or minus I. So in the upper half of the complex plane, we're interested in the case of z being equal to I. We're going to evaluate the residue over there. And notice that because you have z squared plus 1 squared, this z equals to I is a pole of order 2, which means to evaluate the residue of the function f of z at z equals I, we need the limit as z approaches I of the derivative with respect to z of z minus I squared times f of z. And this is a pretty straightforward evaluation. You can factorize the denominator here as z plus I times z minus I both squared. So this means that on the right-hand side, you have the limit as z approaches I of the derivative with respect to z of log z divided by z minus I, z plus I, sorry about that, z plus I squared. And differentiating, we have the limit as z approaches I. Terribly sorry about that. A bit better. Z plus I squared times 1 by z minus 2 times log z times z plus I. Alrighty then, divided by z plus I to the 4th power. So just plugging in z equal to I everywhere, we have 2I squared divided by I. So that gives us 4 times I. Okay, cool. Minus 2 times log I. Now I equals e to the I pi by 2. So the logarithm cancels out the exponential function. We're left with 2 times I pi by 2, with the 2's canceling out quite nicely. Z plus I is just 2I here, and here you have 2I to the 4th power. That's 16. Okay, so that means we finally have 1 by 4 times I, and I squared is negative 1, so that's a plus sign there. Again, 2, that's a pi by 8 in this case. Okay, everything seems to be working out quite nicely. So this here is the residue of the function f of z at z equal to I, and by Cauchy's residue theorem, the integral over the closed contour c of f of z equals 2 pi I times the sum of residues, and there is only one residue here to evaluate, so you have 1 by 4 times I plus pi by 8, and just some multiplication, and you have to cancel out the 2's. You're left with negative pi by 2 plus, okay, pi squared by 4 times I. Okay, cool. So that's what the integral over the closed contour C evaluates to. But again, we have to break down this integral into a few integrals over the various curves involved. There it is, the contour boy again. And the integral over C evaluates out to an integral over lowercase gamma plus 1 over uppercase gamma plus 1 from negative r to negative epsilon plus 1 from epsilon to r. And again, we're interested in these limits. And again, in these limits, the integrals over the gammas sort out to 0. This integral over here becomes an integral from 0 to infinity of log x divided by x squared plus 1 squared. So that's our target integral, I sub 1 in this case. And this integral is worth a bit of evaluation. So this integral in the limit as r tends to infinity and epsilon tends to 0 is the integral from negative infinity to 0 of log x divided by 1 plus x squared dx. So again, we need a transformation from the negative x to the from the x to the negative x realm. So that gives us integral from 0 to infinity dx, switched up the signs there, log negative x divided by 1 plus x squared. And log negative x is just log x plus log negative 1, and log negative 1 is just I times pi. Okay, cool. So that means we have one integral from 0 to infinity of log x divided by 1 plus x squared dx, which is, of course, just our target integral, I sub 1 again. And we have I times pi times this bonus integral from 0 to infinity of dx divided by 1 plus x squared. That's one thing I really like about contour integration. Often in the process of evaluating one integral, you get a bonus integral. So yeah, I find that pretty cool. Even over here, our target integral, the one we started off with, led to another integral, this one here, I sub 1, and we have a third integral. We picked up a third integral along the way. Anyway, that's really cool. That's really nice stuff. So we know what this evaluates to, correct? And this evaluates to negative pi by 2 plus I times pi squared by 4. And on the right-hand side, you have I sub 1 plus I times pi times this target integral plus, again, I sub 1. So comparing the real and imaginary parts, this implies that I sub 1 equals negative pi by 4, and our bonus integral equals pi by 4. Okay, pretty cool. And remember our target integral, I equaled negative 2 pi times I sub 1. But wait, there is something missing, and yes, I remember now. Wait for it, and here we go. we evaluated the integral of f of x from 0 to infinity, but we had to multiply that result by 4. Okay, cool. So that means our target integral I equals negative 2 pi times negative pi by 4 times 4, which implies that the target integral equals 2 pi squared, which is a pretty nice result. It's a very satisfying result after such hard work. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.